Stephen and Matthew for inviting us along today. My name is Sian and I am a registered architect and a certified passive house designer. I'm also the principal architect with Green Being, with Paula down in Queenstown. So in this presentation, we're going to look at some of the solutions. We've talked about the problems, but what we're really aiming for and what we've talked about the last couple of days is creating warm, healthy and energy efficient buildings. In other words, somewhere which is both thermally comfortable, mould free and does not give us any kind of fuel poverty. We've seen that we've got many problems in the New Zealand built environment, but ventilation is not the cure to these problems. And as we heard yesterday, I think Ruth mentioned, and it's something that we've come across a lot, is that many homes are not even reaching this minimum building code standard, as there's ways of fudging through the building code with different methods. And I think most of you in this room will be aware of that and hopefully are not in that category. So our aim is to improve this built environment, and we need to do this with better design and better workmanship. And it's good to see Bill here today. He mentioned yesterday as well that we need to do this by using common New Zealand building methods. So this is not complicated and it's not a major change for our contractors and our designers. So we're going to look at some of those details, but we're also going to look at the main principles behind passive house, which is insulation, airtightness and ventilation. And these are all ways that you can create a healthy indoor environment, and that's whether you go the full way towards passive house or you're just looking at an energy efficient, well-designed building. So we're going to touch briefly on insulation, looking at the avoidance of thermal bridges, and then looking more depth at airtightness and ventilation. Now, I'm sorry to throw a calculation at you right from the start, because I know you've had a huge amount of information bombarded at you, but the reason I'm showing you this is because I want you to know how passive house is intrinsically linked to ventilation. So what we're looking at here is the fresh air requirement per hour per person, which is 30 metres cubed. If you times that by the specific heat capacity of air, and then you times that by the supply temperature, which is 50, and above 50 you're looking at dust carbonisation, which will create a nasty odour, minus the constant internal air temperature of a passive house, which is 20 degrees all year round throughout the house. You get 300 watts per person, and if you assume a 30 metre squared treated floor area on average per person, you get the maximum heating load for a passive house, which is 10 watts per metre squared. Now, if you compare that to what would be an average for, say, a Northland house, you'd be looking at about 30 watts, but that's not necessarily going to get you anywhere near 20 degrees C throughout the home at all times. And if you're looking at a house down with us in Central or in Invercargill, you'll be looking at more like 200 watts. So that just highlights the difference. But we'll come back to this ventilation in a bit. So the first thing is thermal bridge free construction, and we've just looked at why windows, and especially the frame and the thermal edge spacer, which are the most conductive parts of the window, need to be treated very carefully. But in addition to this, we need to look at where the window is actually installed. So this is a detail of a thermally broken frame, which is shown in the centre of a highly insulated wall. And you can see that, you can see that the insulation is taken right up to the frame, and I think most of you would agree that this is not common practice in New Zealand. We often just see a timber window surround with the insulation stopping at this point. So even if we've got a really well insulated wall and we may have employed a thermally broken frame, we're still going to have a gap all the way around that, which is a thermal bridge. And in addition, it's often not made airtight, so we won't have even taped that. And most building sites I go on, before the lining's put on, you can see quite a clear gap around the window where the warm air is going to be whistling out and the cold air is going to be coming in. So this is the main problem that we're experiencing with windows. And this diagram next to it here is a therm diagram. Has anyone used therm in the audience? Yeah. So what this shows, and this is a really basic program, which I think is free. Is it free? Yeah. Yeah, you can download it for free. It's a little bit backward because it's old school technology. I think it was made about 50 years ago. But what it shows you is that different temperatures are sort of different colours here. So you've got obviously the cold on the outside, and this inside temperature of the red colour is 20 degrees C. And we model all our joints and details which we're looking at, which we know will be potential thermal bridges, with this program. And if we see a point where we are at 13 degrees C, we know that that's a real problem because that's where mould is going to form. And if you're looking at passive house, which has, as I said, an internal temperature of 20 degrees C, your internal surface temperatures everywhere in that house, all the linings and the window and any areas around the window that could be thermal bridging, is only allowed to be 3 degrees less than that internal surface, that internal ambient temperature. So you're never going to be below 17.5 degrees for this internal surface, so you need to check those details.